Thank you very much for your introduction. So, good morning, everyone, again. I'm going to talk about a novel finite element formulation that I, from Instituto Superior de Engenharia de Lisboa, and Professor Silberschmidt from the University of Loughborough have developed for the assessment of multi-cracked non-uniform functionally graded beams. So this is the outline of the talk. I will first introduce the problem under study and show its fundamental equations. I will then make some basic considerations on the variational principle that was employed as the basis for the development of the formulation. I will afterwards introduce the finite element formulation itself and show some of the numerical results that we obtained using this formulation. And I will finish the talk by enumerating some conclusions and highlighting some potential future developments. The formulation that I'm going to present was conceived for the analysis of beams with the following properties. The beams have a single or multiple open concentrated cracks. The beams have non-uniform cross sections, which means that the width and height of the cross sections may vary along the axial coordinate. The shear deformation of the beams is taken into account according to the standard Timoshenko's beam theory, and a functional graded material response is considered. Okay, the finite element method, and in particular its displacement-based formulation, very often viewed as the classical or the standard formulation, in which the displacements are regarded as the fundamental unknown fields, has been recognized probably as the most popular numerical method in the analysis of solids and structures. However, when this formulation is applied to beam problems, it leads to internal forces and moments that are not continuous between elements. And this is viewed usually as a drawback in the framework of structural design, because the design is usually based on stresses, which are computed from internal forces and moments, and therefore some sort of averaging procedure may be required. Also, when the standard displacement-based formulation is applied to Timoshenko beams, it may lead to erroneous solutions due to the well-known shear locking phenomenon. On the other hand, mixed and force-based finite element formulations, which have been viewed as alternatives, can be used to naturally avoid this locking effect. Also, equilibrium-based formulations, which in fact are special cases of force-based formulations, can be used to render continuous, entirely continuous internal forces and moments. And the goal of this work is to propose an equilibrium-based finite element formulation that can be used for the quasi-static analysis of functionally graded Timoshenko multi-cracked beams with non-uniform cross sections. Okay, we consider a two-dimensional non-uniform beam with a rectangular cross section, as depicted here, with x the axial coordinate, which varies between 0 and L, the length of the beam. Here, C1 and C2 are general cracks, potential cracks on the beam. U is the axial displacement, W the transverse displacement, and phi the cross-section rotation. The governing equations of the beam can be divided into kinematic equations. Differential equations and kinematic boundary conditions based on the Timoshenko theory. Equilibrium equations, again, differential equations and equilibrium boundary conditions, and also a set of constitutive equations which are here associated with the transversely functionally graded material response. Although both axial and transverse functionally graded material responses could have been considered. Now, in terms of the cracks, they are modeled using a discrete spring approach in which Dirac's delta generalized functions are considered into the beam's flexural stiffness following the idea suggested by Palmeri and Cicirello in 2011. And this means that this flexural stiffness is modified according to this beta parameter, and this beta parameter is a coefficient that is related to the severity of the crack, following the idea proposed by Bilello in his PhD thesis in 2001. So this is the variational principle in which we developed our formulation. As you can see, it's based on the complementary energy. It involves only forces and moments as fundamental unknown fields, rather than displacements and rotations, as we would have if we were dealing with a displacement-based formulation. I will not get into details, but it can be shown that under the subsidiary equations of equilibrium, this complementary energy is stationary, which means that its first variation equals zero, with the kinematic equations retrieved as the stationarity conditions of this potential of this complementary energy. Now, the finite element approximations, they are selected such that the obtained solutions can satisfy in strong form the equilibrium differential equations that I have previously shown. The inter-element equilibrium is enforced by the standard Lagrangian multiplier method. Okay, now in terms of some obtained numerical results, in order to validate the formulation, we considered two numerical tests taken from the work by Palmeri and Cicirello. In particular, a clamped cracked thin beam and a clamped pinned thick beam were considered, both with uniform cross sections and a homogeneous material response. The thin beam is subjected to a shear force and a bending moment. Here is the location of the crack, whereas the thick beam was subjected to a distributed load with a crack position at its midland. Okay, so the problems were numerically addressed using the proposed formulation, using only two finite elements and exact integration. These are the obtained results here in this column, and the reference solutions taken from the work by Palmeri and Cicirello. You can see we have displacements, rotations, bending moments for the two cases, and in all situations we obtained exactly the same results. Okay, and I note again using only two finite elements and an exact integration scheme. Now, a multi-cracked non-uniform functionally graded beam with a transverse tip load. In this case, no reference solution is known. A power law function was considered, and the cross-section variation was assumed as with a quadratic variation. Okay, the beam was considered under the action of shear force, and using this finite formulation with only two elements again and an exact integration scheme, we obtained this for the axial force. As you can see, although there is no axial force applied due to the functionally graded response of the material, we are getting axial forces, shear force and bending moment. As you can see, both distributions are entirely continuous. regardless of this discontinuity here in the shear force, which is due to the applied load. This discontinuity here is exactly corresponds exactly to the shear force applied at the beam. Now the transverse displacement and the rotation fields. As you can see, the kinematic equations are satisfied exactly. So no transverse displacements at the ends and no rotations at the ends. The discontinuities here in the rotation fields are due to the cracks. And it's important to note here at this stage that we have used an exact integration because it was possible in these situations. But if we assume more complex constitutive laws or geometries, then we may require the use of numerical integration schemes. Okay. Now, to conclude, the formulation is variationally consistent with a complementary energy variational principle. It can be used to obtain equilibrated, or in other words, statically admissible solutions, which means that we can get solutions that satisfy in strong form all the equilibrium differential equations and also the equilibrium boundary conditions. The formulation is not affected by the well-known shear locking phenomenon, and it can be used to produce accurate solutions with relatively coarse discretizations. Now, regarding future developments, I would say that the most straightforward ones include the extension of the formulation to the Willett dynamics, buckling, layered beams, three-dimensional beams, and so on. Oh, and that is it. Thank you very much for your attention.